All right, so we're going to take a look at 5.6, the fundamental theorem of algebra. So the first problem we have here says find a polynomial f of x of a degree 3 with real coefficients and the following zeros. 4, -1 plus I, and in this case they only give us two zeros, but because this is an irrational zero or a non-real zero, we know that we can also account for its conjugate, so -1 minus I. So right now, and we're just going to leave this in the factored form, we have our three zeros here. We've got x equals 4, x equals -1 plus I, and x equals -1 minus I. So we're now going to put these into our factored form. So let's say y equals, this would be x minus 4, this would be x minus, and then I'll do -1 plus I, and then here I have x minus -1 minus I. And you can technically write it like this, or if you wanted to simplify it down again, you could. You could also multiply it all the way out, but I'm not going to multiply it all out just because I don't want to spend the time right this second doing all of that. But here we would distribute the negative throughout, so this becomes plus 1 minus I. Distribute the negative, you've got x plus 1 plus I here, and then it would look something like this. Ideally, either one of these are good, acceptable answers. All right, next one down, it says, what quartic polynomial equation has roots of 2 minus 3i, 8, and 2? Well, in this case, this is another one of those irrational roots, so we know we have the conjugate 2 plus 3i here as well. So then we'll do the same thing we did in the last one. We're just going to go ahead and build our factored form polynomial. So y equals, and I'm going to start with the 8, so I'll do x minus 8, then I'll go to x minus 2, then I'll go to x minus 2 minus 3i, and then x minus 2 plus 3i. And like I said, if we wanted to, we could factor all of this out and FOIL it out, but for now, I'm okay with leaving it like this. Alright, here it says, the fundamental theorem of algebra. If p of x is a polynomial of degree n greater than or equal to 1, then p of x equals 0 has exactly n roots, including multiple and complex roots. So basically it's saying that the degree of your polynomial tells you how many roots you should have in the combination of real and then irrational or complex roots. So you're thinking like real numbers and imaginary or those complex roots. Alright, so here we've got an example of our first problem here. It's x to the fourth plus 2x cubed equals 13x squared minus 10x. First thing we want to do is get this set equal to 0, so I'm going to bring the 13x squared and the 10x to the other side. So x to the fourth plus 2x cubed minus 13x squared plus 10x. Oops. Equals 0. So looking at this one's going to be a little different than some of the other examples we see, because right now I can see that there is a GCF amongst all four of these terms. So what I can do is I can reduce, or I can factor out a GCF of x from each one. So I've got x cubed plus 2x squared minus 13x plus 10 equals 0. So right now I already know that one of my zeros is just going to be x equals 0 for this first quantity here. So there's one of my answers. What I'm left with now is I'm left trying to solve the remaining polynomial. X cubed plus 2x squared minus 13x plus 10 equals 0. Ideally, what we could do here is to get an idea of our rational roots that we talked about in the previous section. We could list out all of our different rational roots. That's the p over q. And then we could use our calculator to find at least one, because the idea is to bring this down to a quadratic. So instead of listing out all the p over q values, I'm just going to go ahead and use my calculator And I'm actually just going to find one value. I want to reduce this down to a quadratic. Since we're at a cubic polynomial, we want to reduce it down to a quadratic, so we need at least one rational root. Could we find more than one in the calculator? Quite possibly, but in this case, I want at least one. And so from my calculator, I'm going to get that x equals 2 is one of our rational roots. And so this is the one I'm getting from the calculator. So right now I have 2 of the 4 rational roots I need for the, or 2 of the 4 roots I need for this polynomial. So what I can do with this second rational root is I can use synthetic division to bring this cubic polynomial down to a quadratic. So we'll set up with a 2 on the outside. We'll put our coefficients across the top, 1, 2, negative 13, and 10. And then we'll conduct synthetic division. Drop the 1, this is 2, this becomes 4, this is 8, this is negative 5, this is negative 10, and 0. So we end up with the quadratic x squared plus 4x minus 5. And so this is our new polynomial. This is a quadratic, so we have options now. To solve a quadratic, we can solve by quadratic formula, or if it happens to factor, we could try factoring. In this case, this one actually does factor. 2 numbers that multiply to be negative 5 but add to be a positive 4, well, that's just going to be x plus 5, x minus 1. So that means our 2 remaining zeros, or roots, are negative 5 and positive 1. So in this case, we ended up with 4 rational roots, and we found all 4. Alright, so that's just one type of problem, but let's look at some other types of problems that we could see. Alright, so in the next one, we've got f of x equals x to the 4th plus x cubed minus 7x squared minus 9x minus 18. Notice that this polynomial is a 4th degree polynomial. So in order for us to find all the possible roots, if they're all rational, they're all going to show up in the calculator. But if they're not, then we're going to have to at least find 2 rational roots in order to bring this down to a quadratic, so we could try solving it with one of our other methods, like the quadratic formula. So in this case, I'm going to quickly list out p over q. This is p, this is q, just to get an idea of what my rational roots might be. So p would be plus or minus 1, 3, 6, 9, and 18. Q would just be plus or minus 1. And so then from the calculator, when I go into the calculator and I look at this graphically, I should get that I have 2 rational roots that kind of stand out in this case for this one. Those 2 rational roots are going to be 3 and negative 3. Which are a part of our list, so we're good. So now what we're going to do with these 2 rational roots is we're going to run synthetic division twice, back to back. So I'm going to start with putting 3 outside here. And then I'm going to list my coefficients across the top. 1, 1, negative 7, and negative 9, and negative 18. And then I'll run my synthetic division. I'll drop the first one, so 1. This is 3, that's 4. This is 12. This is 5. This would be 15. This is 6, and so this is 18. So that's 0, so that works. We want it to be 0, because that means our remainder for this time around was 0. Right? And so now what we're going to do is we're going to run a second synthetic division right off of the first one, this time using the other rational root, negative 3. Because at this point, we've reduced our original quartic polynomial down to a cubic polynomial. We need to reduce it one more time down to a quadratic. And so we'll run synthetic division one more time. So this is 1, we get negative 3, 1, negative 3, 2, negative 6, 0. And so in this case, this is our new remainder. And so our quadratic ends up being x squared plus x plus 2. So we were able to find two rational roots in the start. Now we're going to use this quadratic to see if we can't find two complex or imaginary if that happens to be the case. So to solve this, we're going to use the quadratic formula. X equals negative b, so negative 1, plus or minus the square root of 1 squared minus 4 times 1 times 2 all over 2 times 1. In this case, we get negative 1 plus or minus, and here we've got 1 minus 8, so that's the square root of negative 7 over 2, which is going to be, in this case, negative 1 plus or minus I square root of 7 over 2. So then here's our two complex solutions. So right now, all of our roots are x equals negative 3, 3, and negative 1 plus or minus I square root of 7 over 2. Over 2. And so we have 4 roots because we have a 4th degree polynomial. All right, next one we have is g of x equals x to the fourth, or g of x equals 2x to the fourth minus 3x to the third minus x minus 6. All right, so same idea here. If we're thinking of p over q of our possible rational roots, we'll just make a quick list. So it'll be 1, 2, 3, and 6 over 1, 2. And so if we go to the calculator and we look for our rational roots, we're going to find that we get 2 rational roots, because we need 2 to bring it down from a 4th degree polynomial down to something more manageable, like a quadratic. We're going to find that we get 2 and negative 1. So we're going to run 2 and negative 1 using synthetic division. So I'll start with 2. So we got 2, negative 3. There's no x squared term, so we need a placeholder. Negative 1, negative 6. We'll go ahead and drop the first term down. We get 2, becomes 4, 1, 2. So 2, 4, this is 3, and this becomes, 6, so that's 0. There's our remainder, so we're good. And then we'll go ahead and run the second set of synthetic division right after it with our second rational root of negative 1. So we drop the 2. This is negative 2, so negative 1. This is 1. And then negative 3, and then 0. So our quadratic in this case becomes 2x squared minus x plus 3. And so in this case, now we just need to solve this. So we'll go back to the quadratic formula again. So x equals negative b, so that'd be positive 1, plus or minus the square root of negative 1 squared minus 4 times 2 times negative 3, all over 2 times 2. So underneath the radical, we've got 1, and then we've got oh, that's a positive 3. I made a mistake there. Alright, and now we're back on track. So we got 1 minus 24. So that means right now I have 1 plus or minus the square root of negative 23 over 4, which is the same thing as 1 plus or minus I square root of 23 over 4. And so there's our two complex roots. So that means our roots for this problem are going to be x equals 2, negative 1, and then 1 plus or minus I square root of 23 over 4. All right. And then our last problem here, we've got x to the fifth minus x to the fourth minus 3x cubed plus 3x squared minus 4x plus 4. In this case, notice that we have a fifth degree polynomial. So in order to bring this down to a quadratic, we're going to actually have to find at least 3 rational roots in order to bring it down to a quadratic to find any kind of complex solutions. So when we go to this one, and I'm not going to list out P over Q this time, I'm going to kind of jump right into the calculator. And so from the calculator, we're going to find that our rational roots, if we graph this on the y1 line and we look at our graph or look at our table, we're going to get that our rational roots are going to be 1, 2, and -2. So that means we've got to run synthetic division 3 times in sequence to bring this from a fifth degree polynomial down to a quadratic. All right, so let's try this out. So we'll start with 1. So we've got 1, -1, and -3, 3, -4, and 4. So we drop the first, we get 1. 1 times 1 is 1. This is 0. 1 times 0 is 0. This is -3. This becomes -3. This is 0. -4. -4, and then 0. So we've got our remainder piece at the end. Now we're going to run the next one. This time we've got 2. And then we can keep adding these. So we add down, multiply. We get a remainder of 0, so we're good there. And then we do this one more time with our last rational root, which is -2. -2 times 1 is -2, so this becomes 0. 0 times -2 is 0. We get 1, -2, remainder of 0. So our final quadratic is actually something fairly simple. It's just x squared plus 0x plus 1. So x squared plus 1. So in reality, we could use the quadratic formula to solve this, but we don't have to. We can actually just solve this using square roots now. So we're going to subtract 1 from both sides. We get x squared equals -1. Then we can square root both sides. And we get x equals plus or minus the square root of -1, which is the same thing as just I. So our roots in this case, for this problem, are 1, 2, -2, and then I, and then -I, plus or minus I in this case.